This video is going to cover moment distribution method for frames. In this example, we have a T-shaped frame where on the top and the left we have a pin at A, on the top right we have a roller at C, and at the bottom we have a fixed support at D. We have three lovely different loading situations. Up here at the top, this is 4 kips per linear foot. Down on BD, we have 1 kip per linear foot, and we have a point load on BC of 5 kips. EI is going to be constant for this problem, and we want to find all of the internal moments, remembering that counterclockwise is negative and clockwise is positive. So step number 1 for moment distribution method, we want to find all of our reduced stiffness factors. For these, technically, you'll get the same answer if you just assume everything is 4EI over L, but it is a lot faster if you can actually use the reduced stiffnesses. So reduced stiffness is looking at this and saying, well, D is fixed and B is fixed, so he's obviously just going to be our normal equation of K is equal to 4EI over L. But since A is a pin and there's nothing else past A is going to allow for rotation. So technically, BA there is fixed and free to rotate, so that one's going to have a reduced stiffness factor. So that's going to be K is equal to 3EI over L. Same thing for BC, the roller at C is going to allow for rotation, so that's going to be K is equal to 3EI over L. For AB, L is 30, so 3EI over 30 is going to equal 0.1. Again, we can drop the EI. EI is constant. Even if you wanted to keep it there, it will literally all go away as soon as you do the next step, which is our distribution factors. So over here, we also have 3 times EI over L. L is also 30, so that again is 0.1. Though for BD, L is actually 20 feet, slightly different, so we have 4EI over 20. That's going to equal 0.2. So next up is our distribution factors. So again, if you wanted to put EI next to every single one of these numbers, you're going to watch as they all go away in this next step. So for our distribution factors, what we need to do is find out how much of the moment is going to be distributed on each side of a joint. So first up, our distribution factor for the A side of beam AB, that's looking at this side of things. We're looking at the A side, and what we need to do is we need to put that value for K, which is 0.1, on top, and divide by the sum of all the K factors at that joint. And all the K factors at A is, well, it's 0.1 on the right, and on the other side there is no K, so that's 0. So the distribution factor here, again, if you put EI next to both of those numbers, you'd watch as they divide out, our distribution factor is 1. What that means is that anytime you would try to distribute moment over to the pin is going to give it all away, because we can't have a moment at the pin, right? It's an end pin, so it's literally letting it all go. There's not going to be internal moments there. It's just going to let it all go away. So that makes sense. Next up, we can do the same thing, the distribution factor for C on beam CB. And it's going to look the same thing. We've got 0.1 for side C over here, and that is going to go over the sum of everything at C, which will be 0.1 plus the other side. The other side, there is nothing. So again, same thing. The distribution factor at that end is also going to be 1. A little bit different there. So again, roller can completely give away moment. He's not going to take anything. He's going to give everything away. D is a fixed end. So how D is going to work is effectively going to be similar. The distribution factor for D on beam DB is going to be, he's actually going to be 0 over 0 plus 0.2. For D, we're going to be looking at this side of things. D is not going to be giving away any moments. So this should make sense. A fixed support can take everything, right? Because a fixed support has a moment that he's going to be holding on to your beam frame or whatever. So he's going to be resisting any moments that you have. A pin and a roller can't resist any moment in any way, shape, or form there. So, but D can, because of that, this guy's actually going to take everything. It's not a 1, it's a 0. He's going to take everything and not give it away. So if you give him anything, he's just going to hold on to it. That's how he's going to work. Now for B, B's going to get fun because B has 3 different branches for B. So for B, we're going to do them on the other side here. We're going to find the distribution factor for B, and we're going to look at the A side. So for the distribution of B on the A side, that K value is 0.1, right? We're looking at this guy right here. So that's 0.1 over all of the things leading into that joint. So we have the 0.1, the 0.1, and the 0.2, since all 3 of those members all lead into B. So we have 0.1 plus 0.1 plus 0.2. That's going to equal 0.25. Same thing if we're looking at the distribution factor of B on side C. Again, he was also 0.1, and the sum of everything is 0.1 plus 0.1 plus 0.2, so that equals 0.25. And lastly, the distribution factor for B on side D, that is going to be 0.2 over 0.1 plus 0.1 plus 0.2. So that's 0.5. Next, what we need to do is go place this, all this information we just found, place that into our chart right here that we have for our moments. So what we found was at AB, we have a distribution factor of 1. So we've got 1 here. On the BA side, we have 0.25. That's right there. Then going down for BD, he's going to be 0.5. Again, this is going down. It might help you if you write it down here like this, so that you know that he's the going down member. If you want to just remember that he's the one in the middle, that's fine. You know, as we just kind of look, we're going from left down right. That whatever method you got to do to fill out your table properly to make sure that he is distributing properly is up to you. Then I need to leave a little bit of space here, only so that I have space for numbers. But this is the C side of B. And then out a little bit further over here, we have the 1 for the other roller. So that's our frame for our distribution. Now what we need to do is find all the fixed end moments based on our loading. And we have 3 loading situations, so that's really fun. We can start with our first loading situation, which is uniformly distributed here. Right, we can find our loading situation for our uniformly distributed load with 2 fixed ends. So if we go over here and look, we've got 2 fixed ends with uniformly distributed load, and we find that W is, the fixed end moment is WL squared over 12, excuse me, it's WL squared over 12. Again, we do need to remember our positive and negative directions. So we have negative for A, we have positive for B. So again, that fixed end moment, let's write it down here in a new color. Our fixed end moment, this will be number 1, is equal to WL squared over 12. Now W we said was 1 kip per linear foot, L was 20 feet squared over 12. That value is going to be 33.3. So on the A side of things, A is going to be actually at D. If you kind of rotate that picture in your mind there, at D. And oh, we forgot to put D on our little chart over here. D is going to be back here at the bottom, so D. So D is going to be the A side, and the A side we said was negative. So he's going to be down here, negative 33.3, and at the B side it's going to be positive 33.3. Okay, then we have our linearly distributed load of 4 kips per linear foot for AB. So we actually have one of two ways to do this. We've been saying that we need to go to this fixed end moment chart at the back of the book and look for both fixed ends. And as you can see, you're going to have moments on both sides. One of them is WL squared over 20, the other is WL squared over 30. You can do that, or technically, on the right side over here, we have one that has a roller. Well, that looks exactly like ours, right? Except it's flipped. But that looks exactly like ours, and you'll notice that you only have one moment. Well, that makes sense because B is a roller, B won't have a moment. So if we want to make it easier on ourselves, we can totally use this fixed end moment equation. Now, you will get the same answer regardless of which one you use. It'll just be more or less steps. So we're going to use the easier one just for argument here. So our fixed end moment, only on the A side, that's the fixed side, is WL squared over 15. W is 4, L is 30 squared over 15. So that's going to equal 240. Now remember that he is going to be on the opposite side, right? Because he's technically flipped, and he's going to be going this way because technically it looks like this, right? Actually, it looks like that. So he's flipped, so he's going to be actually a positive value. So over here on our positive end, we have 240. And then we also have that point load. That point load's going up. Now you'll notice that none of these point loads are going up. So what that means is instead of, A going this way, A is going to actually go the opposite direction, and B is going to go the opposite direction. So that makes B a negative and A a positive. That's going to be how that works, since you literally just flip the picture upside down. So again, we can do the fixed one, or technically it's a bit more of a disgusting equation, but you can do the one where it's a roller and a fixed end. So again, all that would mean is that A is actually going to be going the opposite direction because P is going the opposite direction. But let's, for sake of argument and ease right now, let's just look at this one here. So it's P times B squared, B is the smaller side of things, times A over L squared. So our third equation for our fixed end moment is we're going to have, and these are going to be different. Okay, the sides are different there, so we have two. On the one side, we have P times B squared A over L squared. And on the other side, we have minus P times B times A squared over L squared. Again, I have the positive and negatives flipped because, again, P was going up instead of down. So what we're going to find is, of course, 5 kip load. B is 20 squared. A is 10 over 30 squared. And then we also have 5 times B was 20. A is 10 squared over 30 squared. So what we find is 22.2 and 11.1. 1. Or we could go out another decimal place if you really want with these values. It's a whole bunch of repeated numbers actually. So now you remember that this guy is negative, right? So that's negative, so we need to go put him where he should be. So over here at the roller we have negative 11.11. Add another digit there. And then we have positive 22.22. So there are all of our moments on our diagram. So what we want to focus on is setting our pin and roller here to equilibrium first, since as soon as they get rid of their moments, they never take it back. Well, the good news is that this guy over here is already at 0, so he's not ever going to take any more. So I'm just going to draw a squiggle there so that, you know, don't try to send anything to him because he's not going to take it. So he's already in equilibrium. Isn't that wonderful? Now we just need to set the other guy into equilibrium. So over at joint C, so at C, we need to do the following. We need to figure out how much we are out of balance, what's the new balance value, what's the distributed moment, and what's the carryover. So our out of balance number is the sum of all of the things in that column. So the sum of it is literally just negative 11.11. The new balance is negative 1 times the out of balance, which is negative 11.11. So that will be positive 11.11. Our distributed moment is our new balance of 11.11 times that distribution factor, which is 1. So that's 11.11. So we come over here and we put 11.11 in that column. Next, this guy is in balance. Congratulations, right? If you sum all that up, it will equal 0. And since he is in balance, he is done. We can squiggle him out. He's not going to take anything else. As far as the carryover goes, the carryover is half of that distributed moment, which is 11.11. So what we're going to find is 5.56. So half of it goes to his adjacent partner, so 5.56. Now, just so that we can clear things up, remember that we did this situation where we have the easier equation. They were both fixed. Just to prove to you that you didn't have to do this, I'm going to show you what happens if you use this equation instead. It's a bit longer, right? But technically, we would get 0 at B. Well, you do end up with 0 at B, right? So this should give us the same thing. So it's a bit longer of an equation, right? We're going to write this puppy out. What would be our fixed end moment using this equation? We have P is 5, over L squared, L was 30, so over 30 squared, times B squared, B was 20, times A was 10, plus A squared, A is 10, times B, which is 20, divided by 2. Kind of a little bit of a disgusting equation, and what you get is 27.8. Let's go take a look. 27.8. Wow. 27.8. It is the same number. It was actually 27.78, technically. I rounded again. I shouldn't have rounded early, right? We were going out to 4 decimals, so my bad. It was 27.78, which is the exact same number. So if you use the long equation because you recognize that you can use this, it saves you 1 step. Just 1. You wouldn't have to figure out joint C. But anyway, just letting you know, total option that you had there. So next, we have joint C in balance. We have joint A in balance. D you can't balance. D never balances because he's a 0. So the only other guy that we have to worry about is joint B. So let's go look at joint B. Oh, you know what? That's probably not a good spot. Let's put him over here. Joint B. First up, we need to find the following things. How much he's out of balance, how much the new balance is, and our distributed moments. So our out of balance. How much are we out of balance? To find that, we have to sum up everything above this line. Everything, all of the things related to that joint. So this guy, and all of these things. We have to sum all of that up above that line. So let's write it out. We had positive 240. We have positive 33.33. We had positive 22.22. And we had positive 5.56. That's a grand total of 301.1. That's a lot. Our new balance is going to be negative 1 times 301.1. So negative 301.1. Our distributed moments, we're going to have multiple, right? Because we have the BA side. We have the distributed moment for the BC side, and we have the distributed moment for the BD side of things. So for each of these, we take the new balance, which is negative 301.1, and we multiply by the distribution factor. So for A and C, it's 0.25, and for D, it's 0.5. So multiply by 0.25 for the C side, 0.25 for the D side, 0.5. And what we're going to find is negative 75.3. It's negative 75.3 and negative 150.6. This is going to be a little bit rough there because this whole thing here does not actually sum up to be 301.1 because we rounded just a little bit there. But anyway, he will be okay. So we need to go write those back down. So we've got here negative 75.3. In the middle, negative 150.6. And on this side, negative 75.3. Now we know this guy is in balance, but we cannot forget to do our carryover. So we should be carrying back, but he has a squiggle, so no can do. We should be carrying over here, but he also has a squiggle, so no can do. So we have to then carry down here. We got to carry, remember, each guy has to go to the adjacent joint. But we've already sent 2 of those guys into equilibrium, so they can't take any more, right? Because they are a distribution factor of 1. They don't take any more once they go into equilibrium. So we just have to send half of him down. And half of him down, you already know what half of him is. That's negative 75.3, right? But anyway, we'll write it down just in case. 1/2 of negative 150.6 is negative 75.3. So we carried half over. Well, since that's an equilibrium, A is in equilibrium, C is in equilibrium, I guess we're all in equilibrium. As equilibrium as possible we can get. So all we have to do now is just sum up everybody's values. So what do we get? We have 240 minus 75.3. We get 164.7. Then we have 33.33 minus 150.6. That's negative 117.3. Then we have 22.22 22, 5.56, and negative 75.3. That's going to give us negative 47.5. Down at the bottom, those two add together to be negative 108.6. Now technically joint B should be an equilibrium, should be. We can check joint B just in case. So we said we have 164.7. We said we had negative 117.3 and negative 47.5. And if we add all that up, it should equal 0. We're actually at negative 0.1, but that's close enough to 0 that it's okay. That's just a rounding thing on our part, which we knew was coming from right here. If you add all that up, that should have equaled 301.1, and 6 plus 3 plus 3 is 2. It's the 12. So that is where that came from. But anyway, close enough, good enough for government work. So that is how you find all of the internal moments for moment distribution method for frames.